The intelligence of a modern large language model is frozen in time. At the exact moment pre-training ends, the model's internal weights are locked. The real world is in a state of perpetual flux. New concepts, companies, and linguistic usages emerge daily. A model trained on data from last year is functionally blind to the events of today. To update that locked knowledge, the standard approach is to build a new model from scratch. That requires spinning up tens of thousands of GPUs for months, costing tens of millions of dollars per run. Without a structural mechanism to dynamically update weights, training large models remains a series of expensive, one-off events. Relying on periodic resets is physically and financially unsustainable. The engineering solution is continual learning, or CL. This approach allows a model to sequentially learn new domains and end tasks, incrementally updating its internal weights without starting over. But continual learning faces a severe obstacle known as catastrophic forgetting. When a neural network is trained on new data, those new weight updates actively overwrite and erase the capabilities it previously acquired. Solving this requires applying continual learning across the entire lifespan of a large language model. This timeline shows a tripartite lifecycle framework with 3 distinct stages: continual pre-training, continual fine-tuning, and continual alignment. Across all stages, engineers face the plasticity-stability dilemma, remaining plastic enough to absorb new information, but stable enough to retain prior expertise. To balance this scale, researchers deploy 3 specific categories of mechanisms. Rehearsal mixes old data with new. Regularization applies mathematical penalties to prevent core weights from shifting. And architecture physically expands or isolates the model's neural pathways. Integrating these tool sets across the lifecycle addresses the fundamental engineering constraints that keep AI models static. We start at the first pillar, continual pre-training, or CPT. This is where a massive, specialized corpus, like millions of legal documents or medical journals, is injected into a general base model. The primary risk here is that flooding the model with hyper-specific terminology can aggressively overwrite the general language logic it originally learned. The first strategy to mitigate this is rehearsal. Instead of training exclusively on the new domain, engineers mix a precise ratio of the original general pre-training data back into the new data stream. The model effectively reviews its old knowledge while learning the new. Strict mathematical scaling laws dictate these mixture ratios, guaranteeing the model converges without degrading its foundational logic. The second strategy is architectural, utilizing a mixture of experts, or MOE, framework to expand capacity. MOE isolates learning. Original, generalist experts are explicitly frozen, while incoming new domain data is routed exclusively to newly initialized, specialized expert nodes. While rehearsal solves forgetting by mixing the data itself, MOE solves it through structural isolation, ensuring new weights never physically overwrite the old. Together, these mechanisms allow a base model to construct a continuously expanding library of domain expertise, fully preserving its foundational core. Moving to the second pillar, continual fine-tuning adapts the domain-specific model to execute a sequential stream of distinct downstream tasks, such as summarizing text, writing code, or solving math problems. The operational challenge here is maintaining high accuracy on the first task, while actively adjusting the weights to master the second, third, and fourth. Applying standard rehearsal at this stage often fails. Storing and replaying real user prompts from past tasks frequently violates strict data privacy regulations. To bypass this privacy bottleneck, engineers use synthetic rehearsal. The language model leverages its own generative capabilities to manufacture pseudo-samples. It creates accurate approximations of old tasks, allowing it to replay memories without ever holding restricted original data. On the architecture side, continual fine-tuning relies heavily on parameter-efficient fine-tuning, or PEFT. In a PEFT framework, the massive base model is completely frozen. To learn a new task, engineers attach incredibly lightweight trainable modules, like LoRa adapters, directly to the network. But standard LoRa has a limitation. If the training data for different tasks overlaps, the separate adapter modules can still mathematically interfere with one another. The advanced solution is to project these modules into orthogonal subspaces, a technique used in frameworks like OLoRa. By forcing the gradient updates for new tasks to be mathematically perpendicular to previous tasks, the system guarantees absolute zero interference between them. This transforms the language model into a dynamic multi-tool. It can seamlessly swap and protect highly specialized skills without requiring a total system overwrite. The final stage is continual alignment. Here, the underlying value system of the generated content must be continuously optimized. Alignment is not a one-time fix. Societal safety constraints, ethical norms, and user preferences shift rapidly, requiring the model to update its behavioral guardrails. Retraining an entire alignment pipeline, like reinforcement learning with human feedback, or DPO, from scratch just to account for a new safety parameter is highly inefficient. Instead, researchers are deploying continual optimal policy regularization, or COPR. This is an efficient reinforcement learning-free mechanism for updating preferences. COPR works by computing an optimal policy distribution and applying it as a strict mathematical regularization penalty. It creates a definitive boundary that physically blocks the model's outputs from drifting into unsafe territory. This rigid constraint penalty forces the network to adhere to new safety boundaries, while simultaneously preserving its fundamental ability to generate helpful, accurate responses. Alignment is an ongoing mathematical negotiation between evolving human values and strict model stability. To determine if this three-stage pipeline is actually working, researchers must empirically measure the model's performance over time. This chart tracks two opposing metrics that dictate the success or failure of any continual learning system. The first is the forgetting rate. This measures pure degradation on old datasets. The architectural goal is driving this line downward until it reaches an absolute zero baseline. The second is the forward transfer rate. It identifies whether the model is developing a foundational understanding that simplifies future learning, rather than memorizing isolated task data. High forward transfer indicates that the model is actively compounding its own efficiency as it encounters new information. A system that achieves high forward transfer alongside zero forgetting demonstrates the transition from a rigid model to one that actively compounds its own efficiency. When continual pre-training, fine-tuning, and continual alignment operate in sequence, the result is a dynamic architecture processing real-time data streams. By balancing plasticity and stability through rehearsal, MOE architecture, and policy regularization, engineers can systematically mitigate the impact of catastrophic forgetting during new knowledge acquisition. The immediate horizon involves extending these frameworks to multimodal models, processing vision and speech, and enabling purely online streaming updates without discrete training phases. If you want to implement these exact PEFT and MOE architectures yourself, head over to the Learn by Doing with Steven YouTube channel for hands-on technical tutorials. Engineering AI models that adapt as quickly as the real-time data they process is a central objective of modern research. For ongoing discussions on these evolving data paradigms, listen to the Steven Data Talk podcast on Spotify and YouTube Music.